In this program, we are going to look at dipole-dipole interactions, hydrogen bonding, van der Waals forces, metallic bonding. In this arrangement of atoms making up acetic acid, there is a very strong covalent bond holding the atoms together. There is another weaker bond called a hydrogen bond holding these molecules in pairs or dimers. And there is a still weaker force called van der Waals between the dimers. If we look around us at common substances, we can see that trees are solid, and water is a liquid. Air is a gas. Each substance has its own melting and boiling point. This gives some idea of the strength of the force holding the molecules in place. So there may be one type of bond holding the atoms in place in a water molecule, but another type holding these water molecules in place in the crystal. These forces are usually weaker. To help us understand how this works, we'll need to look at the newly discovered biscuit atom. This is a single atom. However, this particular type of biscuit atom comes bonded in pairs as a biscuit molecule. The bond is a strong covalent icing bond. It can be broken without destroying the atom. If the molecules are shaken about, they fly and bounce in all directions. This movement is heating, and the molecules are forming a biscuit liquid. More heating, and they would become a gas. Slow down the shaking, which is the same as lowering the temperature, and gravity pulls the molecules down through the bottom of the container. The walls of the container hold the liquid in place. The molecules have a very weak force attracting them to each other. It's a very weak force, far weaker than the strength of a covalent bond. We'll use butter to show the force. The exact shape of the natural crystal structure will depend on the size of the molecules and the orientation of the bonds. If the movement of the molecules is very low, these very weak butter bonds will hold the molecules in place as a solid. Now if we increase the shaking, which is the same as increasing the temperature, the butter bonds will break and the biscuits become a liquid again. This amount of shaking is the melting point of the biscuit crystal. The butter bonds have broken, but the covalent icing bonds are still intact. And of course, if we shook it even more, it would boil off and become a gas or vapor. The butter is still there, affecting the gas slightly. Let's look at substances that melt at temperatures around the range we live at. Because they all melt at quite a low temperature, they must have quite a low force holding the molecules in place. Iodine fluoride is covalently bonded, but the attraction for electrons will be more towards the fluorine. This will lead the molecule to be polar, with oppositely charged poles on each end. The ends will attract, and chains will form. It can happen with more complex molecules, such as sulfur dichloride, as long as they are not symmetrical, and the atoms attract electrons differently. In this case, chlorine takes more than its share of the electrons, becoming slightly negative. If the molecules were placed between two oppositely charged plates, the molecules would all align. In the solid crystal form, they will be aligned in the same way. Of course, the molecules would be in 3 dimensions, not flat like this. When hydrogen is attached to fluorine, oxygen, or nitrogen, it forms a special form of the dipole-dipole interaction called a hydrogen bond. Hydrogen, with its electron away for most of the time, is very small. Other atoms can come very close without being repelled by clouds of electrons. The most common hydrogen bonds are those in water. Let's take a few molecules of similar mass, each with hydrogen, and compare their boiling points. The thing that stands out is the high boiling point of water. This is because water bonds very efficiently. Every hydrogen makes a bond. The water molecule has a negative oxygen and two positive hydrogens. They can link quite neatly to others using all the hydrogens. First, they form a tetrahedron structure of 5 waters. These tetrahedrons form easily into a structure with quite a lot of open space. In ice, this open lattice occupies more space than the tangled mass of water. Water is unusual in doing this, and as a result, ice floats. Other substances sink when they freeze. Hydrogen fluoride has only one hydrogen and does not cross-link as water does. It forms 5 and 6 member rings. Ammonia cannot stack as neatly as water, as its 3 hydrogen tangle without making useful contact, like a batch of untidy chairs. Methane cannot have hydrogen bonds because the hydrogen is attached to carbon. Also, methane is quite symmetrical, so cannot produce a dipole. Hydrogen bonding is present in most of the chemistry associated with life. Organic chemistry. Vinegar is a 4% solution of acetic or ethanoic acid in water. It is made when microorganisms add oxygen to the ethanol in wine or cider. We use it as a food acid because of its sharp taste. After many years of studying its properties and reactions, chemists were able to assign a formula to acetic acid. At first, the molecule with bite was quite simple. However, some experiments were puzzling. The density of acetic acid vapor indicated that the molecules should have the formula twice the accepted CH3COOH. The explanation for this was hydrogen bonds. 2 acetic acid molecules can form 2 hydrogen bonds with one another and produce a double molecule called a dimer. Many of the organic acids exist as dimers. Hydrogen bonding is important to life because it is weaker than covalent bonding. It is useful to have bonds that can be easily broken when needed. DNA is a helical chain that can duplicate itself using 4 building blocks known as bases. They are arranged in a particular order that stores and reproduces the genetic code. DNA can replicate itself accurately because each base will link with one and only one other base. The hydrogen bonds play a special part because when replication is complete, they are weak enough to be unzipped. This is how it works. The chemical soup of life surrounds a single DNA helix, a small part of which you are privileged to see before you. The fickle hand of fate moves the bases around until their hydrogens bond them onto their mate already on the old helix. When the DNA helix has made a copy of itself, it can unzip by breaking the hydrogen bonds. Because they are weaker, they do not break the molecule. And allowing some license for our model, this is how living things grow. The next forces are called by a variety of names: van der Waals, dispersion, London force. We saw that methane could not form hydrogen bonds, yet it will still freeze solid at -182 degrees Celsius. Nitrogen at room temperature is a gas. It must be cooled right down to -196 Celsius before it forms a colorless liquid. It would take -210 before it becomes a solid. Oxygen is very similar. A gas at room temperature, it must be cooled to -181 before it will liquefy to form a pale blue liquid. There must be some butter on the biscuits that causes the molecules to stick together when they are cooled. The force causing liquefaction and freezing seems to depend on the number of electrons. Helium, with only 2 electrons, has the lowest liquefaction and freezing points. It turns to a solid only 1 degree above absolute zero. No one knows exactly what causes these weak forces between molecules. Some think it is simply the attraction of the positive nucleus for the electron clouds of other atoms. Others think the electron clouds are slightly uneven and manage to attract each other. Whatever the cause, this force is the reason organic compounds such as pentane and the octane in motor fuel are liquid at room temperature. Without the butter bonds, or bonds between molecules, they would be gases. So, summing up, if covalent and ionic bonds are about 100 units of strength, hydrogen would be about 10, and the van der Waals forces would be only 1. On the left-hand side of the periodic table are elements with only a few electrons in the outermost shell or energy level. These electrons give 3/4 of the elements the properties of metals. Frozen hydrogen is also metallic. Metals have their own type of bond and form crystal arrays to which any number can join. When metal atoms get together, the electrons are free to move about. The metal atoms virtually become positive ions and are attracted to the electrons between them. The electrons are virtually an electrostatic glue that fills the spaces between the atomic ions, holding them together. All metals are shiny. Most look silver because they reflect all wavelengths. They are actually the color of whatever is reflecting off them. The surface is shiny because of the freely moving electrons. The photons hit the surface and force the electrons to oscillate. The oscillating electrons then give off a photon, just like the original. Thus, light is reflected from any metallic surface. Shine is a metallic property, even when it is liquid. In this gold pour, you will see first the yellow hot molten slag, which is non-metallic. Then molten gold, which reflects the light. It is not quite pure here, as this is only the first stage in the process. Electrons that possess large amounts of kinetic energy in a hotspot can move very rapidly through the crystal and transfer energy to atoms in cooler regions. Because the electrons are free to move, metals are good conductors of heat and electricity. These properties are very similar. The electron blanket allows the metal to be worked into different shapes. If the electrons were fixed in position, the metal would not yield as easily as this. This is sodium metal, being easily molded by force. Pure metals are more ductile and malleable than non-metals. Under a load, the ocean of electrons can move easily, allowing the atoms to rearrange themselves. To prevent the atoms moving as easily, a non-metal can be added to hold the electrons in place. This way, iron can be strengthened by adding carbon to produce steel. All metals can be made more rigid by adding elements from the middle of the periodic table. In the first program, we looked at the ionic and covalent forces bonding atoms into molecules and network solids. Then, in this program, we looked at weaker forces bonding the molecules together to form liquids and solids. Then we looked at metallic bonding and some of the unique properties the free electrons give to metals.